Hi, I hope you enjoyed the gradient descent video. However, the video was a bit long because I took some time to explain the matrix dot products and how they are relevant for machine learning. However, I still feel that I should make a separate video because initially these concepts may take time, and these concepts needs to be very clear. So I think I should make a separate video. What I plan is I will cover the matrix and vector in a little more details during our session or a formal introductory session on machine learning. Okay, in this video, however, I plan to do some linear regression with the real libraries of Python and using some real data on it, so you can get a feel of how you can work on a project, and it would give you a mini project simulation sort of feeling. And I'll also give an indication how this can be developed into a solution, this predictive model, and how you can deploy the model. So let's get started. Hello, welcome back. So in this session we will do some regression on using some real data rather than the dummy data that I have been using so far, and we will use the scikit-learn libraries. So by now I think you should be familiar with how to run the Jupyter notebook. You can go to your command prompt and type Jupyter space notebook, or from your Anaconda prompt on Windows system. So I suggest you run along with me in this tutorial. So this is the link from where you can get the data, and I have got the data in the form of a CSV. Okay, so I have already pre-imported some libraries. So the main takeaway from this with respect to Python programming will be learning the pandas data frame, and we will use less of NumPy here, and we will work with the pandas data frame. You can consider pandas data frame as a programming equivalent of a spreadsheet. Okay. So first step is to look into the data. Okay, let's see. PD from pandas data frame is imported as PD pd.read CSV, and this is the CSV file which I have downloaded. Okay, and here, and let's take it into data.df. Okay, this is not run, this cell is not executed yet, takes some time to execute. Okay, and then okay, so this data is about predicting price of houses based on features in a house. If you see the data frame, it looks like a spreadsheet. You can change the settings of your notebook to see more columns and more rows. So I'll do a head, it prints the top 5 rows. Okay. And we need to do some data exploration or exploratory data analysis first, based on whether we have some categorical columns or not, or whether we have missing data or not. Fortunately, we don't have missing data. We'll explore those problems in a later scenario. For now, we have some categorical columns, that is this grade. You can check, it only takes 5 values. How we can check this? We take grade and we do n unique. So 5 values, but the 5 value, okay, it has only 12 values. Out of how many total? You can see the shape of this data frame shape. Okay, out of 21,000 rows, there are 5 only values, 5 distinct values. Okay, and you can also check the values of what is the column? It's called grade. Okay, grade, and you can check the distinct values. And unique. Unique. And these are the distinct values. However, it seems grade has a linear relation, has an incremental relation, but there could be other categorical values which do not numerically relate. And since our data points, our features will actually map our data point to a high dimensional space, if those values are not numerically related, we need to create a dummy variable for them. I'll explore the concept of dummy variable. For now, we don't need that in this scenario. Okay, it's we will see. So we need to predict, again, let's look at the data frame, and we need to predict the price of the house from these features. So let's take a subset of features, take it in a different data frame. And how do we select? It's like select these features. So let's make a column, let's make a list of columns. you can see the columns by xdf.columns. Okay, columns. So xdf is still not prepared. It's data.df.columns. Okay, but we will take a subset of columns. Let's prepare the list of the column names that we want to take, x columns, and then we take data.df x columns. Again, I have to get better with this typo problem. Okay, so let's take it on something called xdf on another data frame. Okay, and ydf equal to, I think it's the name of the other variable's price, the target variable which we want to predict. Columns, what was the name? Columns. Okay, it's okay, we do that. Okay, it's price. Okay, so y underscore df equal to x underscore df, and we take only the price in ydf. Okay. And what's the problem now? Price is not there. Okay, it's not in xdf, it's in data. It's in data. Okay. Okay, so we will not convert this into numpy, and we will work with data frame. Any library in Python, machine learning libraries, can work with both numpy as well as data frames. Okay, so what do we need to do? The data, if you see xdf, the data is in various range. Okay, so we know what to do. We will first use a x scalar. Okay, x underscore scalar equal to, this is the standard scalar from scikit-learn I have taken, and I will instantiate it. Okay, and I'll create a y scalar. Okay, so we have created the x scalar and the y scalar, and before we go ahead, we need to split our training data, so that we can reserve some amount of data for testing. Okay, on which we have not trained, which we will use as an unseen data. So we use this train test split functionality to split our x data and y data into x train x test and y train y test. Okay, in the ratio of 33%. So we reserve 33% of data. Beautiful. This, why should we use this function? Because it uses it draws the data randomly, and also it maintains some proportion related to the y data. Okay, so that all the similar sorts of data are not put in the train or not in the test. Okay, so we do that, and now we scale. Now we fit our scalar on the x train as x train scale to x scalar, and we have already used it earlier. Fit transform. And y train scaled is equal to y scalar dot fit transform y train, and we have to fix the dimension of y with reshape. Okay, so we have prepared the scalars and converted also, and we will use fit on the test data also. So x test scaled x scalar, and we'll not use fit transform, we'll just use fit on x test, and y test scalar not scaled y scalar dot fit. So y is also now, both train and test data is now scaled. I'll show you why we need to reshape y, because it is a one-dimensional data. and we need to make it in the shape of a matrix. Okay, here. So y test, if you see, it misses a dimension here, and reshape adds makes it 71331 or 17133. That is required for the training. So now we prepare our linear regression with this library. We will not implement ourselves, we will use the library implementation, and we will use lg.fit. Okay, test y, not x test scaled, and y test scaled. Why did we scale it? Because our data was in different scales. Even if we look at all the values, if we just quickly have a look, if we look at xdf, see, all are at different scales, some in thousands, some in ones, but after scaling they should be in similar scale. Scaled. Oh, something wrong. When scaled, what is? Argument must be a string or a number, not standard scalar. We have passed the standard scalar somehow. Scalar, it transform string. Okay, here's the problem. I have used fit here, it should be transform. Okay, and this should be transform. We use the learn parameters to transform this. Okay, and we should not be using test here, we should be using train here. Okay, so our linear regression has learned. So how do we predict? We will predict on the same data that we used to learn and see how our values deviate. Okay, predict on x train. So it will predict all the training data, x train scaled, and we will take it on predict train. And similarly we will take it on predict test. X test scaled, and let's compare how our predict test, these are all our predicted values, and we had our y test, but we cannot go, okay, y test scaled. Okay, but we cannot compare one by one, so we will use another library here. And it is called scikit-learn metrics.mean squared error. If you remember, we were using mean squared error, the square of the difference, and then summing them over and taking the mean of all the observations. Okay, and we took our gradient on the mean squared error to calculate the change in weights. So we will use, there's a library to calculate mean squared error now. We will not implement the formula. So we first see how it's we will use the y train. These are the real values and these are the predicted values. Okay, and this is the error, and this is the test error, the predicted test values. Well, the errors seem to be close. That means that there's no variance, but the errors are high, and that means there is some bias. So what is bias and variance? And that is the reason I have kept this image over here. So this is a high dimensional data, but let's bring it down to 2 dimension for understanding better. So we have assumed that the line, that we can fit a straight line. Okay, and it might be possible that it's not a straight line, it's something like this. It can be a circular line, or it can be some, so that is the bias. So we cannot fit a straight line. So we need to consider polynomial regression. Maybe we might need to raise them to some powers and combinations of them, or we might need to include more features. We have only taken a subset of features for this demo. Okay, and what is variance? Variance is when we consider them when we fit every point during the training, but it is so much fitted that a slight variation in the testing data, the line is not able to predict. It has fitted too much with the existing data. That is called variance. And how do we address variance? We use something called regularization. Okay, and regularization adds some sort of penalty when it tries to fit too much. Okay, so normal linear regression library does not allow us to add the regularization parameter, but we will use some sort of another regression library called the reach. Okay, and if we create a reach object, reach, and you pass it with some parameter. What is the parameter here? It's called alpha. You can use other optimizers also, like gradient. Like normally this one I think does not use gradient descent, but you can use gradient descent here. Okay, with optimizer to say G, or there are other list of options you can find in the documentation. And then let's okay, it's not optimizer, it's the term is something else. We have to see in the documentation. Okay, yes, the term is called solver. Okay, okay, but and the rest is same. You can use like this. However, here you will not benefit much. The problem is not variance, the problem seems to be bias. Okay, how do you realize whether it's a bias or variance? If the training results errors are low, but you see a high test error results, high test case errors, that means it has fitted well with the training set, but the test errors are high. That's variance. And if both are high, that it's if you have a high training error, it's most probably it can be both bias or variance, but it's most probably bias you have to first address. Okay, so and we will use some persistence mechanism of Python to store these models. Okay, let's see, pickle is a persistence mechanism, and you can do pickle.dump to store this RG on your file system. And you open a file like this in Python and name it predictor.pickle. You have to open it in write mode and in binary, so you put WP, and then you also have to save the, not only this, you have to save the scalars, because whenever a data comes in, you have to use the scalar to first scale it down. Okay, scalar, and you have to store the y scalar also, because once you predict after scaling down, you have to rescale it back. Okay, you can check ls.pickle. You can run Windows your command prompt commands using experimentally from Jupyter notebook. See, these are saved. Okay, some were saved earlier, the ones with the A. This is the ER things are stored now. Okay, and in a later module you could use this, you could load this using pickle.load. You can load this, you can pass these names, and you into some variable predictor again. Okay, and you can use this to predict any data, and you can create a service around this data to solve your problems or to predict any housing price. Okay, so we move into another notebook, and here we have not written. I have somehow just prepared that notebook with all the necessary imports, and here we have a prior knowledge of which are the columns and what sort of data frame we require. So we have been provided the data in this format, which is looks like a JSON, right? So we have been given a data with bathrooms, bedrooms, and the dates, ID, latitude, longitude, price, some data has been given and we want to predict. This is a completely unseen data. So actually this is something that looks like a JSON, but in Python this is called a dictionary. Okay, this is a type of a data structure which works on the key value pair. So if this is the data and you can access bathroom like this, house info, and you give the key, it's like a map in Java if you are familiar with that. Okay, so it works on a key value pair. Okay, so this is how let's assume like we are implementing an API and someone has provided, and the API is called with this sort of JSON which we managed to convert into a dictionary. So we will write the inferencing code now, or the prediction code now, using the pickles, right? So we will first load the regressor predictor, and we will use now pickle.load. So what was the name of the file that we used? This is house.pickle, and we will use, okay, I've used the codes twice, and here, okay, we have to put it in an open. We have to open a file. This is the file reading, and we have to read it in binary read mode. This is how we read a file. Okay, I open the file and load it to a pickle. We have to load the xscaler also. Pickle.load, and let me copy this. Okay, let me put the second one, that's going to be RB, and let me copy this. And finally also put the y-scaler. Okay, and the three variables are not loaded. I again made a spelling mistake here, and it's the C is typo. Okay, now we know our predictor. We have trained the predictor to predict on data frames. It cannot take a dictionary. Okay, so we have to convert this dictionary into a data frame. Okay, so it turns out that if you give a list of dictionaries, data frame is created with these as the column names. We don't have a list, but our predictor can predict a list of data, not only for one data it can predict, but however we will add it to a list. How do we add to a list? We can take a list variable and append it, but if we just put it, this creates a list. It's a list of it. So we put it inside a box bracket, and okay, so here it is, and you see this is how a list variable looks like. It's now a list variable. So it's a list. You can take it in a variable also. X equal to input equal to input is okay. However, that is not required. We will just convert it into a data frame. Data frame. I'll get better with these typos. Okay, so we have this converted into a single row data frame, right? And we select the columns from there, because we are only going to predict on these fields, right? Let me type in X columns. Okay, and here, so we have this data, and how do we predict? I can take it in a variable, let's say prediction input. I prefer doing sometimes things in one line altogether, but for better understanding and visibility, this is a better approach. Let's print it, because Okay, and let's first scale it, transform, scale it to our predictable sizes that we can feed into our predictor. Okay, and we scaled it. See, it's a scaled value. Okay, we don't need to print it, and we feed the scaled value. Let me do it in one line now in the predictor. So predictor dot predict, we put this value here. Okay, and this is our y, but this is our scaled down y. We need to scale it back. So y predicted y scaled, we get the scaled down version, and typo again. Okay, and now use the inverse transform on y. So this is our predicted price. So we can write a function out of that. Yes, predict price, and that function should take in our house info, which is a dictionary info, and it should take in our predictor, take in our x scalar, and it should take in our y scalar. It's not scalar, actually it's scalar. It should all be e. Okay, and we do this here, and then we do this. We can do this directly, and we can return. So we have a function now, and we can write an API in Python. So there are many ways of writing an API in Python. You can use a library called Fast API, or you can use a library called Flask, and you can use these libraries to create an API which can be called over the web using a GET request. And if you have these pickles, you can create an API which if provided with a JSON of this format, can call this function where it could read and pass on these predictors and x scalars along with the input, and it can return the price of the house. So that is the rest of the deployment, but you generally get the idea. So how you can do the prediction and deployment of your model. Okay, so I think you enjoyed this first hands-on with some sort of real data. Maybe in a different hands-on we could show also the creation of an API in Python, but that's not directly related to the data analytics. But since we also want to learn Python and do an end-to-end solution, so we will also visit that. Okay, thank you.